There is a name for space travel's greatest success story, and it's not James Webb. No, since for the past 47 years, the two Voyager probes have been traveling across the wide reaches of space, providing us with new information about uncharted cosmic worlds. The identical sister probes have now even traveled into interstellar space, one of humanity's most remote outposts, and they have revealed to us that the solar system's furthest regions are far stranger than previously believed. However, how can we account for the odd discrepancies that the probes have detected at our home system's threshold? What about the enormous, enigmatic, wrinkly structures that lie in the heliosphere? In retrospect, 1977 almost looks like a different era. In fact, it was the year that the cult movie Rocky won 3 Oscars. Jimmy Carter was elected President of the United States, and the last execution in France by guillotine took place. The launch of the two NASA space probes, Voyager 1 and 2, however, is another event that occurred in 1977 and continues to this day. Voyager 2 was the first spacecraft to leave Earth. It departed on August 20, 1977, with the goal of exploring the mainly uncharted regions of our outer planetary system. 16 days later, on a different course, Voyager 1 followed. Nobody could have predicted at the time that this would be the first signal for the mission that would endure the longest in contemporary space exploration. That Voyager 1 and 2 would eventually have an astounding distance of 24.63 and 20.59 billion kilometers, respectively, from the Sun was not anticipated at the start of the program because, as was previously mentioned, the probes had really only set out to gather new information about the outer planets of the solar system. In fact, initially, the venture was not even under a lucky star. From the start, communication with Voyager 2 was problematic. Thankfully, though, NASA specialists were able to swiftly address the issues and clear the path for the historic mission, which set off for uncharted worlds. Our planetary system's outer representatives are now visible to us in a previously unheard-of level of clarity thanks to the James Webb Telescope. However, the circumstances were entirely different nearly 50 years ago. We knew very little about the far-off planetary worlds when Voyager 1 and 2 launched into space. Consequently, the initial items on the study checklist were related to the Jupiter and Saturn systems, and the terrestrial experts were immediately complimented with a large number of photos and thorough measurements. Our knowledge of the famous ring planet and the massive gas giant was elevated to a whole new level in the process. Voyager 2's mission had a few more interesting stops in store, but it was time for Voyager 1 to strike off for interstellar space. After a correction action in the spring of 1981, the probe proceeded to Uranus, arriving on the planet on January 24, 1986. To be clear, Voyager 2 was already 2 times longer than it had been initially estimated to be. The spacecraft, however, not only examined Uranus closely, but also found 10 previously unidentified moons of the distant ice giant, suggesting that it didn't give much thought to any earthly forecasts. Neptune was to be the next destination, and this time it was to be the last chapter of the scientific expedition. The more than 9,000 images of the outermost planet in the solar system captured by Voyager 2 at the time amounted to a visual farewell because there were simply no plans to pass by any other locations. But in addition to carefully photographing its surroundings, the probe updated the star charts with 9 previously unidentified satellites. This was to include a detailed study of Triton, the largest of Neptune's moons, and one that was already known at the time. Voyager 2 revealed that its diameter is only 2,760 km, rather than 5,000 km as previously thought. Additionally, it discovered that there were remarkably few impact sites on the satellite's brownish-white surface, and that several geysers are inactive here, frequently shooting liquid nitrogen into their surrounds. We must go back a little to 2012 in order to attain the next major milestone of the Voyager program, arrival in interstellar space. Given that this far-off region, which is no longer within the reach of the Sun's powerful arm, is not precisely nearby, this is not shocking. Dust and ionized atomic and molecular gas are the 2 most significant components of the interstellar medium that fills this far-off cosmic region. The galactic magnetic field and electromagnetic radiation complete the interstellar medium, even though these elements collectively make up the interstellar matter. In 2012, Voyager 1 crossed the solar system's edge, and in November 2018, its sister probe did the same. The satellites are making all-time observations here, just as they used to do on our planet's doorstep. Experts have had the unique chance to examine and contrast the interstellar medium at two distinct sites, though, because the probes are not traveling in the same area. Therefore, one of Voyager 2's primary responsibilities is to compare and contrast the data gathered by its twin probe. In fact, a lot of data from Voyager 1 should be verified in this manner, such as the particle density in interstellar space. But when we examine the ways in which the probe's measurements vary significantly, the situation becomes even more intriguing and perplexing. However, we must first comprehend the structure of the solar system's boundaries in order to fully comprehend the Voyager discoveries. In essence, the Sun is surrounded by a dynamic network of magnetic field lines that are hidden from view. These, in turn, serve as conduits for the so-called solar wind, which is the release of electrically charged particles into space. The solar wind finally reaches the interstellar medium after spreading throughout the solar system. However, the interstellar medium and the solar wind do not mix well, much like water and oil. We know from the Voyager data that the heliosphere, a bubble formed by the solar wind in the interstellar medium, stretches around 18 billion kilometers from the Sun into space. Finally, interstellar space begins at the heliopause, the furthest boundary of this zone. Almost nothing was known about this region prior to Voyager 1 crossing the solar system's barrier. The results the probe transmitted back to Earth in this area, however, left scientists both astonished and perplexed because so many of their forecasts had turned out to be incorrect. For instance, the interstellar magnetic field is actually nearly 3 times greater than previously thought, which implies that the heliosphere is under 10 times as much pressure from the interstellar particles as is depicted in the theoretical models. Even while the Voyager 1 data were revolutionary and new, they had a significant flaw: they were not complete. This was due to the straightforward fact that since the 1980s, the device used to measure plasma temperature has been flawed. But the researchers were even more eager to know what data the probe would gather as it got closer to the heliopause because the counterpart aboard Voyager 2 was still operational. As of right now, we know that the probe slowed down and heated up while the surrounding plasma increased its density. The interstellar medium reaches temperatures of over 30,000 C beyond the heliopause, which is much hotter than scientists had anticipated. However, the temperatures surrounding the space probes are remarkably low due to the very thin and diffuse irregularity of the plasma. Additionally, Voyager 2 discovered that the plasma moves in the reverse direction from interstellar space into the heliopause. Compact extensions of interstellar particles were encountered by Voyager 1 as it passed through the heliopause. Oddly enough, however, its sister probe encountered a type of particle stream that stretches over 150 million kilometers into the heliopause. The fact that Voyager 1 crossed a region where the solar wind significantly slowed down, 3 billion kilometers before the heliopause, is equally odd. Overall, though, these odd discrepancies just hint to the mysteries that need to be resolved in the future with relation to the solar system's periphery. For instance, we now know that the heliopause is surprisingly wrinkled, even though we are unsure of its precise structure. Princeton University researchers used the data to reconstruct the shape of the heliosphere and the heliopause after observing a massive increase in solar wind pressure of nearly 50% in a matter of months. The astonishing outcome was that the heliopause has enormous folds that stretch tens of astronomical units into space. In summary, the average distance of 150 million kilometers between the Earth and the Sun is equivalent to the length of an astronomical unit. Thus, we are discussing folds that span several billion kilometers. Although Botox won't help in this case, maybe the knowledge that the specialists have gathered regarding the history of the wrinkle structures may. These are specifically caused by high-energy particles that clash with the solar plasma after returning from the heliopause in waves. As a result, we are better equipped to understand that the heliosphere is a dynamic phenomenon that continuously billows, dips, and unfolds again, rather than a static and unchanging thing. Because the fold structures continue to expand as soon as the solar plasma smooths them again, the cosmic folds are actually chasing after the Voyager probes. Voyagers 1 and 2 will escape the folds in their necks despite the probe's ancient age, because they are just traveling too quickly to be captured by them and return to the expanding heliosphere. However, because of the pursuit of the folds, the probe's distance from the heliosphere is not increasing as quickly as one may first think. If the distance between your finger and the subscribe button suddenly decreases considerably more quickly than you would anticipate, we would be overjoyed. Please feel free to subscribe and give us a thumbs up so you don't miss any more of our videos. See you shortly.